In this section, we're going to talk about cylindrical and spherical coordinates. So we're going to start with cylindrical, but to get to those, we're going to have what is hopefully a review for most, if not all of you, of polar coordinates. I'm sure you've had some polar coordinates, at least briefly, in your mathematical career. So let's take a look at the old two-dimensional XY plane here. And let's say we have some point out here. Now, we actually have, as you know, a nice way we can get from the origin to that point. And we have a way we can describe how to get from the origin to that point. And that is we say, all right, I'm going to go out a certain number of units in the x direction, the positive x direction. We would call that, well, say x number of units. And then I would travel up y units until I get to that point. And so we would say this point has a coordinates x, y. And so if you say to somebody, I got a point in R2 in the two-dimensional coordinate system that has these coordinates x, y, and you put numbers in there, they would know how far to go to the right or left and then how far to go up or down to get to that point. And so you have this sort of four-way traveling. You can go, right or left, up or down, west or east, north or south, if you think about it that way. But if you're going to give your directions that way, in terms of north and south, west and east, you have to have those directions available. Well, interpolar coordinates, what if you don't have north, south, east, and west available? Well, you need another way that you can get to that point. And that way was to start at the origin and say, all right, I'm going to first of all turn until I get my body looking straight at that point, and then I'm going to just walk directly out to it. And that's another way to describe how I get to that point. I'm going to turn theta units and then walk out r units till I get to that point. And so another ordered pair in polar coordinates will be r comma theta. I walk out r units in the theta direction. Not many people know this, but actually polar coordinates were invented by a guy who worked at a gas station on the North Pole. People kept coming by asking directions, and he couldn't tell them, go east or west because everything was south. So, okay, so anyway, there's a couple of things we need to know. X squared plus y squared equals r squared. We do have a right triangle here. So we have these equation that will convert from rectangular, that's what we call the xy coordinate system, to this is polar, and we're going to add a third coordinate to get to cylindrical here in just a second. But a couple other things. The cosine of theta is adjacent over hypotenuse, x over r. And so the way we usually remember this conversion, x in the cylindrical system is equal to r cosine theta in the polar system. The sine of that angle is opposite over hypotenuse, so that's y over r, which tells me that y is equal to r sine theta. We also see that the tangent of theta is y over x. Okay, so on to cylindrical then, and let's take a look at those. Basically, it's going to be a three-dimensional version of polar. We're just going to add in our third dimension the same way we do when we went from xy to xyz. We're going to go from r theta to r theta z. So let's take a look then at our three-dimensional space here, R3, with x, y, and z coordinate axes. And let's say we want to get to a point. With our rectangular coordinate system, we'd walk out x units, then over y units, and then up z units, and get to our point right there. And of course, that kind of makes a box, as you can see. Okay, so that's not a very good box, but I think we get the idea. All right, well, there's another way we can do that, and that is to say, first I'm going to start at the origin here, rotate my body until I'm looking to the point where it would project onto the xy plane. So I'm going to walk then r units out until I'm directly underneath or above the point. If the point is in negative z territory, I'd be above it. And so this is, again, theta right here, and then I'm just going to go up or down until I get the point, and that's going to be z. So our rectangular then, of course, in R3 are the ordered triples, an x coordinate, a y coordinate, and a z coordinate. Well, then we have our cylindrical, and that's just simply r, theta, and z. So we just add the z in. The z is the exact same as it is in rectangular. So we still have those same conversions then. X is equal to r cosine theta, y is equal to r sine theta, z is equal to z, x squared plus y squared equals r squared, and tangent of theta is y over x. So let's take a look at an example or two of converting from, say, cylindrical to rectangular. So let's suppose we want to convert from cylindrical to rectangular. We should be able to go both ways, but let's try it this way first. And let's look at this first one here. And let's suppose we have 5 comma pi comma 3e, and we want to go from that to rectangular. Alright, so a good thing to do is to sort of sketch out where this is. So what are we going to do here? Really, we start with the second coordinate, at least I do when I'm thinking about it. I'm going to rotate pi units, pi radians I should say, off the positive x-axis. Okay? So I'm going to do that. So I'm going to rotate pi radians. That puts me facing down the negative x-axis. I'm going to walk then, so there's pi. I'm going to walk 5 units in that direction. So let's say that's 5 units right there. And then z is the same, so I'm going to go up 3e units. Here is my point. Now, how would I get to that in rectangular coordinate systems? Well, looks like if I went 5 in the negative x direction, didn't change my y value at all, and went up to 3e, I'd be in business. So just by simply sketching it out, we can see how to get to that point in rectangular coordinates. It'd be negative 5 in the x, 0 in the y, 3e in the z. Now, if you can't see that as well, you can always use those conversions. X is equal to r cosine theta, as we said. That's 5 times the cosine of theta, which is pi. Cosine of pi, that's right, negative 1. And so that's negative 5. Here we have y equals r sine theta, which is 5 sine of pi. Sine of pi is, that's right, it's 0. 5 times 0 is 0. So we get an x of negative 5 and a y of 0. And of course, z is z, 3e is 3e. Let's try one more here. Actually, this time, let's go a little bit different direction. Let's convert from rectangular to, put a C there, cylindrical. And here is our coordinates 7, negative 7, 6. Alright, so here again it is helpful, I think anyway, to draw a picture. See where your point is, and then you should be able to find your r and your theta, and of course your z is going to be the same as 6. So I'm going to go 7 down the x-axis, 7 units this way, negative 7 down the y-axis, and then 6 units up. So 7, negative 7, and 6. Alright, so we're going to sort of look then at the xy plane here. Let me just pull that part out, because really we just need to get the polar coordinates of this point right here, where I go 7 units to the right and 7 units down. What is this angle? Actually, let me do that in sort of a different color so we can see where it's going to lie here. What is this angle off the positive x-axis? Well, now remember, we travel this direction. This is a reference angle, since we have the same sides here, of pi over 4. We would actually set to negative pi over 4 if we go in the negative direction this way. Or going in this positive direction around, we have 7 pi over 4. So we actually have a couple different options. I can tell you to rotate in the counterclockwise positive direction, 7 pi over 4. And so one way to say it is going to be, well, 7 pi over 4. Oh, wait. What's r going to be? We need to figure out r, don't we? Yeah, well, if this is 7, this is 7. This is 7 square root of 2, right? So r is 7 square root of 2 by the Pythagorean theorem. Theta is either 7 pi over 4 or negative pi over 4. And, of course, z is equal to 6. So either 7 root 2, 7 pi over 4, 6, or 7 root 2, negative pi over 4, 6. Now, if you wanted to convert these using the formulas, you'd have to use the fact that the tangent of theta is y over x, which in this case is negative 7 over 7. Theta is the inverse tangent of negative 1. If you put that into your calculator, it's going to kick back negative pi over 4, because remember that the inverse tangent, the negative 1 there, only returns an angle between negative pi over 2 and pi over 2. So you'll get that negative pi over 4 one. But either of them tell you how to get from the origin to that point. Alright, let's look at one more example here of rectangular to cylindrical. And let's start with our rectangular coordinates of -2, 2, and -3. So this one, again, it's actually pretty similar. Here we're going to go -2 in the x direction, positive, sorry, -2 in the x direction, so my x extending out that way, +2 in the y direction, and -3 in the z direction. So going down here, there's my point right down here, but again, what we care about is the polar coordinates in the xy plane. So let's pull the xy plane out here. And we went -2 in the x, +2 in the y, -2, +2, and so this is going to be a reference angle then of 3 pi over 4. So, yeah, the reason I wanted to do this example is because you can't always count on just putting it into that formula that the tangent of theta is y over x, because in this case, as with the previous example, this would be 2 over -2, which is -1. If you take the inverse tangent of -1 in your calculator, it's going to kick back pi over 4, negative pi over 4. That's not the angle we want. We want 3 pi over 4. There's, of course, more than one angle that has a tangent of -1. Inverse tangent always returns the one between negative pi over 2 and pi over 2. We want this one to be negative pi over 4. Actually, we want 3 pi over 4 is the angle that we want. Okay, and then, of course, this is going to be 2 root 2 using the Pythagorean theorem. And so our r, theta, and z is going to be equal to r, which is 2 square root of 2, theta, which is 3 pi over 4, and of course z is z, -3. Alright, I think that's probably enough with cylindrical. Let's take a stab at spherical coordinates. Now these are so named because they very nicely describe spheres, and we'll see more of that later on. But here's how we're going to take a look at these things. Okay, so here is our point in 3 space x, y, and z. And let's say at some point, let me draw it in the x, y, z here first. Okay, so let's say this is our point. So again, one way to get there is with those rectangular coordinates, x, y, and z. Now here's another way to get there. Here's what you're going to do. You're going to start here at the origin, and you're going to have a couple of angles. The first angle is just like the theta in cylindrical coordinates. You're going to rotate until you are facing where the point would be projected on the xy plane, and that's theta. Same theta as in cylindrical. Okay, then what you're going to do is you're going to look straight up the z-axis, and you're going to rotate until you are looking straight at the point. So you're looking straight up, and then you start counting off radians as you rotate your head down towards that point. That angle is what is called phi. And then you walk out a distance of rho units to that point. So you rotate your body theta units, or theta radians, bring your head down phi radians, then you're facing the point, walk out rho units until you get there. Alright, let's take a look at this then. So we have spherical coordinates, and they're going to be given in this form of rho, theta, phi. So those three numbers will uniquely describe a point in spherical coordinates. Now, what are some of the relationships we have? This purple line here you can think of as the r back in cylindrical coordinates, and notice that x squared plus y squared plus z squared, so x squared plus y squared plus z squared is rho squared, a couple applications of the Pythagorean theorem. Now we also remember that, well, you can see that in terms of theta here, x is equal to r cosine theta, but what is r equal to? If you look down here, r is, you can make a copy of r up here, and you can think of r as being the opposite side of this right triangle formed with an angle of phi. So r is equal to, let's see, rho times the sine of phi. And so x is equal to r cosine theta, which is equal to rho sine phi cosine theta. Y is equal to r sine theta, which is equal to rho sine phi sine theta. Now, how about z? How are we going to define z? Well, z could be translated over here to this axis, and so the cosine of phi is the adjacent side of z, cosine is adjacent side of z over the hypotenuse of rho, and so z itself is equal to rho cosine phi. Z is rho cosine phi. Alright, so though we have those equations, that'll help us convert back and forth. So let's try a couple of conversions here. Rectangular to spherical first of all. Let's say we want to convert 0, 4, root 3, comma 4 from rectangular, suppose those are rectangular coordinates, to spherical. Alright, so again, it's helpful to draw a picture the best you can anyway. If you can visualize where this point lies in R3. 0, 4, root 3, 4. Now this is x, y, and z here. So I'm going to go out 0 on my x-axis. I'm going to go 4 square root of 3 on my y-axis. And then up 4 on my z-axis. Okay, so let's draw in our line here. Here's our point. Now, if you think about that, 4, 4 root 3, this right here is going to be our distance rho. And I hope you recognize this as a 30, 60, 90 triangle. This being 30 or pi over 6, this being 60, this of course being 90. And if that's the case, then the hypotenuse is always double the shortest side. Or you can use the Pythagorean theorem if you like. Or, I mean, it's going to be 8. Another way you can do it is say rho squared is x squared plus y squared plus z squared, which is, well, 0 squared plus 4 root 3 squared plus 4 squared. That's 0 plus, let's see, 16 times 3 is 48, plus 4 squared is 16, is 64. Rho squared is 64, so rho is 8. Now, what about theta? Well, theta is the angle that we rotate off the positive x-axis until we're facing that point where it projects to on the xy plane, which is right there on the y-axis, so that's pi over 2. So theta is pi over 2. Now what about phi? Well, phi is how far we rotate off the positive z-axis. Alright, so how are we going to figure that out? Well, you can see that you can make this same triangle here. Let me sort of copy it over here. 4 square root of 3. This is phi right here. So the tangent of phi is opposite 4 square root of 3 over adjacent, which is 4. That's the square root of 3. So phi itself is the angle whose tangent is square root of 3. This will return an angle between negative pi over 2 and pi over 2, which is good, even though notice that phi can only be between 0 and pi over 2. I should probably say that up here, that phi is limited between 0 and pi. We can't go past the negative z-axis because then we could just come back on the other side. Alright, angle whose tangent is square root of 3, which of course is just pi over 3. So that's the angle there. And so our coordinates then, rho, theta, phi, are 8 pi over 2, pi over 3. Okay, let's do one more conversion here. Let's say we want to convert these coordinates from spherical this time to rectangular. Alright, so let's try and get an idea of where this point lies in R3. So rho is 2. Remember what these are. This is rho here, this is theta here, this is phi here. So what I'm going to do is I'm going to come pi over 3 off of the x-axis, and that'll project me out to where the point lies in the xy plane if I was projected onto it. But then I'm going to come down pi over 4 units in that direction off of the positive z-axis. So there's that point there. Here's the point I'm looking at, and we're going to go out then 2 units. Okay, so I've got a right angle here. Let's make that a little bit better. Right angle there. And I've got a pi over 4 angle here, pi over 3 angle here. Okay, so from that pi over 3 we should be able to figure out x and y, I think, without too much trouble. Let's see. Well, I'll tell you what, let's start by finding z. Z, remember, is rho cosine of phi. So that's 2 times the cosine of pi over 4. That's 2 times the square root of 2 over 2, or just square root of 2. So that, of course, makes sense. This is square root of 2 right here. That means this is going to be square root of 2 right here. And now I think, yeah, we shouldn't be too bad here. If you take a look at this triangle, I'm going to pull this one out. I've got this here. Let's see, how do I want to look at this? That's fine. Let's do it this way. Here, here, and here. This is the square root of 2 units right here. So let's see, this is pi over 3. This is 90. That means this is pi over 6. And the hypotenuse is always twice the shorter side. So this is square root of 2 over 2. And then the pi over 3, the side opposite the larger angle in a 30, 60, 90 is square root of 3 times this. So that's square root of 3 times the shorter side. That's square root of 6 over 2. Now we can use the formulas to figure these out as well. X is rho sine phi cosine theta. That's 2 times the sine of pi over 4 times the cosine of theta. What's theta? Pi over 3. That's 2 times the square root of 2 over 2 times the cosine of pi over 3, which is a half. So that's equal to square root of 2 over 2, just as we had surmised. Y is equal to rho sine phi sine theta, which is 2 times the square root of 2 over 2 times the sine of pi over 3, which is square root of 3 over 2. So that's square root of 6 over 2. Now, just a quick note, too, of why they call them these coordinates. Suppose I want to say I have a cylinder of radius 2. Well, the equation of that in cylindrical coordinates is going to be simply r equals 2. Because if you think about that, that's going to be all points that lie a distance of 2 units away from the origin if it's projected onto the xy plane. So that's going to look like this. Okay, and it's just going to be everything, if it was projected on the xy plane, would be 2 units away. It's a very simple equation to describe a cylinder. If I want to describe, say, a sphere of radius 2, the equation for that is simply rho equals 2, because this is all points that are distance 2 away from the origin. Remember that yeah, that's what this is describing. So this is just a sphere. Every point is distance 2. All right, should be in good shape for your homework. Your password for 9.7 homework is an oldie but a goodie, whilom. It just simply means former. As in, once you get done with this homework assignment, it'll be a whilom assignment, a former assignment. Does that make any sense? Whilom is what it is. Good luck on your assignment. Let me know if you have any questions.